everyone, I hope you find it well. Today's lesson will be electron configuration. This lesson is quite of a reminder from the previous lessons we've done in the first semester. The objectives that we have to define the electron configuration, discuss the rules in writing electron configuration, write the full and abbreviated electron configuration of the elements from any period on the periodic table, illustrate the orbital diagram for each atom based on their electron configuration. What did you remember? How will you describe the location of electrons revolving around the nucleus of an atom? What are quantum numbers? What do these quantum numbers describe? How do we compute for the maximum orbitals per energy level? How do we compute for the maximum number of electrons per energy level? What can you see here in this picture? We see a man climbing up a ladder or climbing down a ladder. What can you see? Bohr's model of the atom. Each orbit has a given number called quantum number. Bohr's orbits are like steps of a ladder, each at a specific distance from the nucleus and each at a specific energy. Or, as we said it, the levels. Electron configuration of the atom. The arrangement of electrons in an orbital of an atom is described by a number that designates the number of the principal shell, a letter that designates the number of the orbital, a subscript that designates the number of electrons in the particular subshell orbital. For example, 2p4 indicates 4 electrons in the p subshell or sublevel and second shell or second level. 3d8 indicates 8 electrons in d subshell of the third shell. The rules of the electrons, we have done that previously, so we can remind them. In order to write the electron configuration, we need to know the rules. 3 rules govern the electron configurations: Aufbau principle, Pauli exclusion principle, and Hund's rule. Using orbital filling diagram at the right will help you to figure out how to write them. Start with the 1s orbital. Fill each orbital completely and then go to the next one until all of the elements have been accounted for. Aufbau building up principle. Electrons in an atom occupy first the lowest possible energy levels and or orbitals in order: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, etc. No more than 2 electrons in any orbital ever. The next rule is Pauli exclusion principle. No 2 electrons in the same atom can have the same set of 4 quantum numbers. For example, the maximum number of electrons in an orbital is limited to 2. The spins have to be paired. We usually represent this as an up arrow and a down arrow. Since there is only one s orbital per energy level, only 2 electrons fill that orbital. Quantum numbers describe an electron's position, and no 2 electrons can have the exact same quantum numbers. Because of that, electrons must have opposite spins for each other in order to share the same orbital. Pauli exclusion principle. For 1s orbital, maximum of electron is equal with 2. 1 electron, level 1, sublevel 0, magnetic sublevel 0, spins plus 1 per 2, and etc. Hund's rule. Hund's rule states that when you get the 2 degenerate orbitals, you fill them at halfway first, and then you start pairing up the electrons. What are degenerate orbitals? Degenerate means that they have the same energy. So the 3p orbitals on each level are degenerate because they have the same energy. Similarly, the d level and f orbitals are degenerate too. Remember, each square must have 1 till 2 maximum electrons. Exception to the rule: there are 2 main exceptions to electron configuration: chromium and copper. In these cases, a completely full or half full d sublevel is more stable than a partially filled up sublevel. So an electron from s orbital is excited and rises to a 3d orbital. As we said in the previous lessons, we said for copper we take one electron from the level s and we put on the d level to make it complete or half complete. Arrangement of electrons in the atoms of the first 10 elements. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. This is the electronic configuration. Simple problem. Determining the electron configuration. Problem. Using the periodic table, give the full and condensed electrons configurations. Partial orbital diagrams showing valence electrons and the number of inner electrons for the following elements. Remember, the valence electrons were the electrons that were in the outer shell. We have potassium, molybdenum, lead. The plan. Use the atomic number for the number of electrons and the periodic table for the order filling electron orbitals. Condensed configuration consists for the preceding noble gas and outer electrons. Solution. First, we fill the configuration. We have potassium that has atomic number 19. 1s2, 2s2p6, 3s2p6, 4s1, which means it's in the fourth level, sublevel S, group 1. Condensed configuration is equal with argon, 4s1. Partial orbital diagram, this is it, and there are 18 inner electrons, the other levels. For molybdenum is the same thing, full configuration, 1s2, 2s2p6, 3s2p6, 4s2p6. After we complete the 5s2, we complete the sublevels D. First we complete the 4s, then the 3d, then after we complete the 5s2, we complete the D. Since the D is not fully or half completed, we take one electron from s2 and put it on the D level. So it's 45, 5s1. Same thing goes for lead. Here is an activity. Write the expanded full electron configuration of the following elements: calcium, potassium. Write the abbreviated electrons configuration for the following elements: aluminium and copper. Illustrate the orbital diagram for rubidium. An assessment. Write the electron configurations full and abbreviated for each of the following atoms: scandium and gallium. Determine what elements are denoted by the following electron configurations: krypton and xenon, which elements do correspond with them. Illustrate the orbital diagram for number 4. Reminder, deadline for the homework is on Friday. Send them these days. If not, you will get a bad mark.